All right, so you've been hitting those StatQuest videos, huh? Diving into the world of neural networks.
Looks like backpropagation and gradient descent have got you curious.
Yeah, those can seem a bit intimidating, all that math swirling around, but honestly, once you get the hang of it,
It's actually pretty elegant, isn't it?
it is. And these videos, they have a knack for breaking things down so well. It's all about, at the core, fitting a curve to your data.
Right, but instead of just a straight line, we're talking about a curve that can bend and twist, capture all those nuances.
Exactly. Like, imagine trying to fit I don't know, a piece of string to a bumpy rock.
Okay, I like that visual. You got to adjust the string, right? Make them follow all those peaks and valleys.
And that's essentially what a neural network is doing, finding that perfect fit.
And the key to all that bending and shaping, activation functions. They're like the building blocks of our curve.
So instead of just any old curve, we've got these special pieces activation functions we can put together in different ways.
Right, and the way we connect them, like how much influence one has on the other, that all comes down to the parameters, weights and biases.
Okay, so it's like adjusting the knobs on a sound mixer, right? Each parameter tweaks how those activation functions are combined.
Love that analogy. And remember that drug dosage example from the videos?
Yeah.
Showed how even tiny tweaks to those parameters.
Yeah. The dosage example.
It could completely change the shape of our prediction curve.
It's about finding that sweet spot, the dosage that gives you the best results, and then you scale that up, more inputs, more layers in your network.
Things start to get really powerful really fast.
But even as it gets more complex, the core idea is still the same, right?
Absolutely. Yeah. Finding the best fitting curve for your data. And that, my friend, is where backpropagation comes in.
So we've built up our neural network, right? Got those activation functions humming, parameters ready to be tweaked.
Like we've got all the ingredients for a delicious cake, but now we need to bake it to perfection.
And backpropagation, that's our oven, right? It helps us fine-tune everything, find the best possible combination of those parameters.
Exactly. We're looking for the perfect recipe, the one that gives us the tastiest predictions.
Getting hungry already. But before we start baking, we need to figure out what perfect even means in this context.
Right. We need a way to measure how well our current curve, our current recipe, actually fits the data.
Like, are we talking about a Michelin star cake or something that just tastes okay?
Pretty much. That's where the sum of squared residuals comes in. It's like our taste test tells us how far off our predictions are from the real deal.
Okay, so the smaller the sum of squared residuals, the better our cake, the more accurate our predictions.
Exactly. And to find those perfect ingredient ratios, those optimal parameter values, we use a bit of calculus.
Calculus. You said we didn't need to feel the math.
Don't worry, it's not as scary as it sounds.
Oh.
Think of it like this. Remember that last bias term, B3, from the video?
The one that seemed kind of tiny but could still mess things up if it was off?
That's the one. We can use calculus, specifically something called the chain rule, to see exactly how much changing that one bias impacts our sum of squared residuals.
So it's like we're not just randomly throwing ingredients around, we're carefully measuring how each one affects the final product.
Precisely. And the chain rule, that's just a fancy way of breaking down a complex calculation into smaller, more manageable steps.
Like a recipe within a recipe. But once we have those calculations, what do we do with them? How do they actually help us find those perfect parameter values?
That, my friend, is where gradient descent comes in. It's like our trusty GPS guiding us towards those optimal values.
So we've got our GPS, gradient descent, ready to guide us, but we're talking about finding the best value for every single weight and bias in our network now, right?
Exactly. It's not just about tweaking one ingredient anymore. We're trying to perfect the entire recipe.
So how do we even wrap our heads around that? It's like baking a cake with 1,000 ingredients.
Well, imagine instead of one GPS, we have a whole fleet of them.
Okay, a GPS for every single ingredient. That's a lot of navigation.
And each GPS is telling us how much changing that one ingredient, that one parameter, will affect the overall taste of our cake, or in our case, the accuracy of our predictions.
So we're still using the chain rule, right, to see how each parameter impacts the sum of squared residuals, our measure of tastiness.
Exactly. It's like we're running a sensitivity analysis for every single knob and dial in our network.
Okay, so we have all this information. We know how much each parameter affects the overall error. But now we've got 1,000 GPS signals to follow. How do we make sense of it all?
That's where gradient descent really shines. Remember that visualization from the video, the lost landscape? Instead of just going downhill, we're now navigating a vast mountain range.
Right. We need to find the lowest point in this entire range, the valley where our error is the smallest, across all those parameters.
And all those GPS signals, all those partial derivatives, they tell us which direction to move, how much to adjust each parameter to keep descending towards that valley.
So the learning rate, that's still our trusty walking stick, right? Making sure we don't tumble down any steep slopes.
Exactly. We need to find that sweet spot, taking big enough steps to make progress, but not so big that we overshoot the valley altogether.
This is blowing my mind. But the cool thing is we don't actually have to do all these calculations by hand, do we?
Not at all. That's where tools like PyTorch come in. They're like our super-powered calculators handling all the heavy lifting behind the scenes.
So we can focus on the big picture, designing the network, understanding the principles, and interpreting the results.
Absolutely. But even with these powerful tools, it's still so valuable to grasp the underlying concepts.
Like you said earlier, you don't need to be a mechanic to drive a car, but understanding how the engine works makes you a much better driver.
Exactly. And speaking of understanding how things work, remember that attention concept the video touched on. It's a core mechanism in those advanced models like ChatGPT.
Yeah. It's wild, right? How those models seem to focus on certain parts of the input. Like when you're reading a sentence and certain words just jump out at you.
It's mind-blowing. And while we won't dive into all the details right now, just know that it's all built on these fundamental principles we've been discussing. Matrix calculations, gradients, optimization. They're the building blocks of some truly incredible AI.
So we've gone from tweaking individual knobs to navigating a vast multi-dimensional landscape, all in pursuit of the perfect prediction.
And that, my friend, is the beauty of neural networks. They might seem complex on the surface, but at their core, they're just sophisticated curve-fitting machines, guided by the elegant principles of calculus and optimization.
It's been quite a journey. We've demystified backpropagation, tamed gradient descent, and even caught a glimpse of the magic behind attention mechanisms.
And hopefully this deep dive has given you the knowledge and the confidence to keep exploring the ever-evolving world of AI.
Exactly. Thanks for joining us on this exhilarating adventure through the heart of neural networks. Until next time.